Okay, today we're talking about storing sorted strings. So we're going to go through a slew of different, very, very cool compression techniques. To give this context, last year we talked about succinct sets. So in particular, we looked at, given you have n integers and you're selecting them out of a universe of size u, how do you encode them and how do you do that as space efficiently as possible? And one of our observations was that sorting, in some sense, both of the compressed versions of the sets that we saw were relying on the integers being sorted. And the sorting is really what allowed us to do the compression effectively. So the two techniques we looked at were delta compression with golem codes and Elias-Fano. And with the delta compression, right, the idea was just to encode the distance between adjacent integers in a sorted order. And because they're sorted and they're presumably close to each other, we don't have to spend too much space on the encoding of the distance. With Elias-Fano, right, it was a similar encoding, but the intuition was a little bit different. Here, the idea was just partition the space, put entries in a given partition, and then implicitly encode the greatest common prefix for entries within a given partition. Right, so different intuitions, but both were effective. Here are the assumptions we used last time. Last time, we assumed that our keys are coming from within a bounded universe. We used a unique integer key to identify every item, and we also assumed that there are no duplicates in the set. So today we're going to ask, what if none of these assumptions actually hold? Right? And in many realistic situations, they don't. So in particular, for today's class, we're assuming that the universe is unbounded. We are assuming that you can use a var length string to identify any one of your keys. We can allow duplicates to happen today. And in addition, let's just kind of crystallize a few more assumptions. Today, we're actually storing key value pairs. Right? So last time we just compressed integers keys. Today, every variable string key also has some sort of variable string value attached to it. We're going to assume that this data is static. The staticness of the data is what's going to allow us to achieve good compression. And we're also going to assume that all of this is in storage. Right? And that's going to really motivate a lot of the design that we're going to see. Yet last week, we didn't actually make any assumption about whether the data is in memory or in storage. Okay, these are our assumptions. As we're gonna see, there are a lot of, these are not random assumptions. There are many applications that are designed to navigate these particular assumptions. So these are actually very realistic. I'll show you an application shortly. But first of all, let's just look a little bit more closely at the significance of assuming that the sorted data, these sorted strings, are going to be stored in storage. So as you probably remember from last year or last semester, or if you've done some of the background that I suggested that you do for this class, reading and writing from storage at units of less than something like 4 kilobytes just doesn't pay off. Right? And the reason is, if you're, okay, sorry that these are kind of flipped, but if you're using a disk, head movement really dominates your I/O overhead. So if you're reading at very small units, you're not really taking advantage of sequentiality at all. And if you're using an SSD, right, you have a minimum granularity of 4 kilobytes anyways. So if you're doing any operation at a smaller granularity, you're not really winning anything. You're still reading and writing at 4 kilobyte chunks. Okay, right. So for this reason, as we saw last semester, database organizes their data in pages. These are typically 4 kilobytes each. And that's the granularity at which we read and write. Okay, so what we're going to look at is how to actually store our variable length strings and values in a sorted order along these pages, right? Such that if we're looking for a particular key value pair, we can just access a given page and not read too much redundant stuff. Okay, happy so far? Good. So what's our application for all of this? So our application is actually LS entries. Right, so this is a very common data structure, exists is the backbone of many key value stores in industry. And the core idea is this data structure tries to optimize insertion overheads to storage by buffering all updated data in memory and flushing it to storage in large sorted chunks and then sort merging it. Right, and the idea is it's only performing sequential writes, so it's very optimized for storage. Okay. So how does this structure work? Just to give you a sense, there is a buffer. Whenever the buffer fills up, we take its contents, sort them by key, flush them to storage, right? So we can get these runs of sorted strings in storage, and we want to restrict their overall number so that we don't have to search all of them. So we implement these sort merge operations, right, to restrict the number of sorted components. Right? We organize them in levels. A lookup has to search the different levels from smallest to largest. Right, the most naive way of searching these is doing some sort of binary search, right? But this binary search in storage will typically be way too slow. So typically we have these fence pointers, which contain the first key of every page in storage, right? And these, so if this is a run and the run contains a bunch of pages and each page contains a bunch of data, here I'm just representing the key as an integer, but each one of these keys is actually a string. We can do a binary search over the fence pointers, and then access the relevant page in storage that contains the key we're looking for with just one IO. Make sense to everybody? Cool. Okay, so what we're going to look at today is how to actually compress the run, in a sense, assuming that the run contains key value pairs, which are unbounded strings. Okay, and why compress? Why do we actually care about compressing, this LSM tree data in storage? Does anybody have a sense? Yes?
How does it take up less space? But only if it takes up less space, we can do fewer options.
Yeah, so exactly. So you have two great reasons. One of them is it allows us to actually exploit the storage capacity of the device better. The second one is by compressing the data, we actually get to read and write less from storage because what we're reading and writing is smaller in size, right? So we optimize IO as well that way. There's actually a third reason, and the third reason is that SSDs die as a function of the number of writes that you issue to them. So by having compressed smaller writes, you actually elongate the lifetime of your SSD and you can save costs. Okay, so these are all our motivations. What are the downsides of compression? Sorry? We might lose random access. That's completely correct. We're going to see a lot of ways to kind of avoid that from biting us throughout the lecture. One other reason? You have to use CPU cycles to actually do the compression and decompression. So, okay, so I only have one of those here, but the first reason is correct too. The point, though, is that here's the importance of our assumption that data is in storage. So we're assuming IO is the overhead here, meaning that compressing and decompressing the data, right, that's done in CPU. That's typically not going to be as expensive as the IO overheads. So in some sense, we can do that almost for free. I guess we can assume that. I mean, it's actually not for free, but yes, but we have this big other overhead that we can kind of mask these overheads by. Does that make sense? All right. So our case study for today is actually going to be the page formats, or in some sense, the SST format, the file format, let's say, in RocksDB. So RocksDB is an LSM tree-based key value store. All that it's doing is, in some sense, storing sorted var length strings. So we're going to look at what it's doing. And by so doing, right, we're going to see a lot of techniques emerge. And it's really fascinating to see how all these techniques actually kind of stack up on top of each other. It's also nice because this is a system that's actually widely used in practice. Now, I'll make a disclaimer. I'm describing RocksDB to the best of my knowledge. The kind of design that I'm showing you here, I think it was pretty accurate 2 years ago. I don't know if they've made any changes since then, but at least this is up to date as of 2 years ago. This is a super interesting design, and any misrepresentation that I make of this design is completely unintentional. Okay, so here's our agenda. So as you see, we're going to cover something like 7 techniques throughout the lecture. Okay, so the first thing I want to talk about is we're assuming here that we're storing variable length data. So there's a question of how to actually size the pages of the database. So here's something naive that you can do, right? So here you're packing a page, right? This is a 4 kilobyte page. And let's suppose that this is data that we've already filled up. And now, we have this other entry, and, we're considering whether to insert into the remaining empty space in the page. This is while we're actually creating the page, right before we write it to storage. So as long as the entry fits, we might as well just, kind of add it to the free space here. That's a no-brainer. But what if the entry is too big to fit in the remaining free space that you have? Right, our entries here are variable length sized. So, okay, so that's annoying. Any ideas? Any reactions? Yeah. Yeah, you could put it in the next page, exactly. So that's the first option. Seal the page and just waste some space, right? But what's the problem here? Well, one of the problems is that we're actually, like, our whole motivation here is to encode this data as succinctly as possible. So if we're not going to systemically lose some space at the end of this page, and we might as well lose potentially a lot of space, right? And you can imagine that every entry is just a little bit more than half the size of the page. Right, then we're going to lose half the storage space. So this is not that good. Okay. The advantage here, though, with this approach is that it makes sure that our pages are all aligned with SSD pages. So it's at most 1 IO to read each page. Okay. 1 plus, 1 minus. Okay. So what's the other thing that we can do? Is that a question?
I know it was just something else.
All right, fine. Okay, so what we're instead going to do is actually allow having variable length pages, and we're going to forego alignments. But as we're going to see, it's not going to be as bad as you think. So here is the actual policy that RocksDB implements. It defines a parameter called block size deviation, and let's say it sets it to 10%. And what that parameter says is, suppose that we have a big entry incoming. This is kind of a simple policy. It just says, if I have less than 10% left space in the page, then I'm just going to seal the page as a smaller than 4K page and just write the entry to the next empty page. Okay. On the other hand, if I have more than 10% extra space, I'll put the entry here and I'll just have a page that's larger than 4 kilobytes. Okay. So, maybe not the most sophisticated thing. I mean, in particular, this policy doesn't actually take account of the size of the entry. Yes?
Like the previous one, where it's like, if it's less than 1%, you seal it. Even if the entry is very good, we're supposed to seal it in this.
Say that again?
Like, if we have an entry that fits within 1%,
yeah,
even that we just like forgo it and go to the next one.
Oh, no. If the entry fits in the 10%, then you put it in. Right? It's only so both cases that I just described are in case the entry is too big. And then whether you put it in or not depends not on the size of the entry itself, but on the amount of whether you have more or less than 10% free space in the page that you're trying to insert to. Okay. So anyways, so far everything is pretty right. These are pretty intuitive policies. The trade-off is pretty clear. This is actually what RocksDB does, right? And as a result of this, the pages are approximately 4 kilobytes, but there's always going to be some variation. So here is an illustration of this, right? The pages can be a little bit more. So if these are the SSD pages and they're fixed size, the database pages are, exhibit some variation, and so they're not going to perfectly align. Okay, so the issue here is, well, the good thing is we're not wasting any space here, but the problem is we are foregoing SSD page alignment, and so for every entry that you're trying to retrieve, you might potentially have to do 2 IOs as opposed to 1. Now you might think, okay, these are sequential IOs, not such a big deal. That would be true on disk drives, but in SSDs, the difference between sequential and random reads is not actually that big. So it does kind of bite you to have to read 2 adjacent pages on an SSD. If you like, it would be better if you didn't have to. Yes.
It's like if there is an page is too large, then for the next page, it will be smaller to like say to align with the SSD pages.
As in, if this one is large, then the next one might not be so large.
Yeah, like be smaller than the original page. Like that's what I see from there.
I think that's just coincidental. I think that like depending on like whatever sizes of entries you actually get, it might not be like this. But you're actually on a good track here because so far I'm kind of describing kind of a depressing picture. We're trying to save space, but we're, messing up our read cost. In all of what I've described, try to put things together. Are things really as bad as I'm presenting them here? Is there any reason for hope for our query cost? So what's going to happen after we compress these pages?
The entries are smaller. And if the entries are smaller, they don't fit in a page.
Yep.
It's a smaller portion.
Excellent. That's exactly right. So suppose that we're now going to start compressing the pages. Let's imagine in this figure, I'm imagining a compression rate of 4. That means the entries are smaller, right? And so by kind of averaging it out, more of them happen to fit in a page. And you can kind of predict if your compression rate is X, that only 1 plus 1 over X pages on average. Right. So this is actually going to be our average read cost, right? 1 plus 1 over X. Why is that? Because if our compression rate is X, we can kind of roughly assume only 1 over X of the entries are crossing between page boundaries. Only for those pages, we'll have to do 2 IOs, but for most pages, it'll just be 1 IO. Yes.
This is assuming a particular size. It seems to be assuming that entries were originally the size of one.
No, so each one of the, okay, sorry about any illustration confusion, but each one of these rectangles is assumed to be a page which contains multiple entries.
Each one of those rectangles. But then why are the LSM pages so much smaller than the SS pages then? Why wouldn't we just like keep the LSM pages the same size but then allow there to be one?
Because if we are, because then, so you could start, okay, so it's a good point. You could start with an even larger than 4K page and then try to compress it and aim to compress it to 4K. But then you're still going to get the alignment issue and you're going to be doing something like 2 IO per page or per entry. Does that make sense?
So since the page is not this size now, are we gonna store a jump table? If we're the page is
Yes, actually. So the fence pointers that I described actually in the background section, these are actually going to be pointers to the start and end of like particular pages. So we can still access, we still know exactly where each page begins and ends. We have that data in memory. We just have to read it in a non-aligned way, which might result in 2 IOs, but in most cases, after compression, 1 IO.
Also, is it a limit on the size of one? Because it's too large, might not fit even in one page.
There might be internal limits, but I'm not actually sure that any of the, so there are going to be some aspects in this design that do restrict like the number of entries that you can have. We're going to see them actually later. But generally, I think that even if you had one key that's, like 4 kilobytes, I think this design would support it. Okay. Any other questions? Okay, so this is just kind of a high level design point. Now let's look at the internals of each one of these pages. All right. Yeah.
Actually, I think so. You mentioned that if there is less than 10% left, we drop it, we seal the page, right?
Yes.
Why not we don't consider that and then just direct it that?
So like, why not? Like, why just add the entry?
Then why don't we just use that 10%?
I mean, I suppose you could. The policy that RocksDB is using is in some sense, it's just like a very simple policy. So what you're proposing will result in slightly bigger pages on average, I guess.
Then this argument kind of mitigate that, right?
Yeah, so so this would mitigate it, but I mean, I still feel like I'm not sure that it would lead to such a big difference. So that means that rather than getting a trade-off of 1+, so with your design, it might be slightly higher than this, but not by much. So at the end of the day, you can actually play with all of this by just kind of tuning the target page size anyways. I can see that would be the same thing. Okay. All right, let's move on to delta compression. Okay, so the idea with delta compression is to, we saw this last time as well. The idea is to remove common prefixes of adjacent sorted keys. Now, last lecture, we saw this in the context of, I guess, Elias Spano. Not Elias Spano, sorry, the Golem coding. But that was with integers. And how you do it with strings of variable sizes is a little bit different. So suppose you have the following strings. Let's consider how to delta encode them. First of all, note that this is the first string. This string is sharing a 5-byte prefix with the first one. And the third one shares a 4-byte prefix with the second one. Okay, so what shall we do? How should we actually encode this to remove the common prefixes? Yeah.
Maybe some sort of try.
A try, okay, a try is a nice idea. What would be potentially the downside of a try?
They are sharing different amount of prefixes. Then you kind of have to first mark terminal nodes and then
Right.
pointer jump.
Yeah, there might be a bunch of pointers there, right? There might be a bunch of random access. Let's assume that we're not going to use a try. Let's try to still encode this sequentially. Yeah.
Shortest common.
Out of all of them, what would you be losing anything then?
You would potentially be losing, like, if you use A, B for all three, then you would potentially be losing central state in C.
Yes, that's right. That's exactly what we'd be losing. So we're actually going to try to, you're kind of talking about greatest common prefix across the whole page. That's what B trees do. We're going to try to do a bit better here. Okay. So what we're actually going to do is add 2 different values to every key value pair in the page. These are going to be called shared bytes and non-shared bytes. And right, so they now exist for each key value pair. And here's what they mean. So the shared bytes means how many prefix bytes are you actually sharing with the key that came before you? And the unshared is how many new bytes are you introducing after the ones that you're sharing with the one before. Okay, so it's might be more interesting to look at this entry here. This entry is sharing 5 different bytes with the entry before, and only 2 characters are new after that. Question?
There need to store shared bytes. Can we just figure out total bytes shared?
Okay, great question. Why do we still need to store the unshared bytes? Does anybody? Exactly. You don't know what the length of this key is.
Oh, so store.
Yes. Yes. So we need both. Okay, does this make sense? All right, good. So now we're going to move these redundant prefixes, and we've saved ourselves a lot of space. So that's nice. Okay, so any issues so far with this encoding? Yes. No random access. We're going to address that soon. There's another issue. How do we actually encode these fields of shared and unshared bytes?
You can still store them as characters and use some state characters for them.
Okay, yeah, so you're kind of hitting a nice point that we don't really want these to be fixed length, right? And why? So imagine that each one of these is actually fixed length. Let's say that each one of them is L bytes, right? So we're going to be spending something like 2L bytes for each key. The issue here is that, first of all, this is potentially a big overhead. Like, imagine that L is 4 bytes. That's a big overhead for every key value pair. But also, if we set that to be small, then we are restricting the maximum size of keys that we can compress or that we can actually store. Right? Does that make sense? And this is either wasteful or restrictive if we're using fixed length integers to encode this. So instead, we are going to be doing something a little bit cooler. You suggested using an escape character. Okay, so what would that look like more precisely?
Essentially, like to reserve I guess, for the first two numbers. Then you have maybe like an escape, the first number, an escape, the second number, an escape. And then after the second number, after the second escape, you know that that's the actual content from the string.
Okay, yeah, and how would the escape look?
It would be a single character.
Okay.
Like you might preserve, I don't know, like if it's ASCII, like 255 or something.
But then you're spending one whole byte as an escape for each one of them, right? So your encoding is like for both of them is like at least 2 bytes, right? Yeah. So, okay, so that's still maybe a little bit wasteful. Can we do better? Okay, so allow me to introduce to you the var int, right? And the var int is just, it's a byte, but only 7 bits of that byte actually contain useful information. And 1 bit is used to indicate whether another byte is coming. It's kind of what you suggested, but just using 1 bit as a delimiter instead of more. Okay, so this is called a continuation bit. And here is what the whole thing looks like. So imagine we're trying to encode 123. In binary, it looks like this. This is just 7 bits. So in this case, there is no additional bits. And so we just use 1 byte to encode this. On the other hand, let's suppose we're encoding a larger number. So this number now, that's the binary representation for this number. That doesn't fit in 1 byte or in 7 bits. So we are going to use 2 bytes. 7 bits fit completely in this byte, but 4 bits fit here. We have some spare space here. What should we do with this spare space? Just add zeros. And then, all right, the continuation bit here is going to be 1 because we have 1 more byte coming. Here it's going to be 0 because this is the last byte of this integer. Good. All righty. So we're going to lose something like 1 divided by 8, this fraction of the space. But the nice thing that this allows us to do is we are now very, very flexible, right? And we can encode each one of these shared and unshared bits using usually just 1 byte for each one of them. So we're going to waste something like 2 bytes for each key value pair for these. But we still have the flexibility to encode larger keys and larger keys if we need to. Most of the time, we won't have to because each one of these counters can encode 2 to the 7 values. Right? So as long as our key value pair, as long as our keys are no longer than 128 bytes, we're fine. And usually they're not going to be that large. This is a pretty large size for a key. Okay, so keys are typically less than this, and so for the most part, we're spending 2 bytes per key. Is there a question?
Let's say technically if keys are larger than the 64 and you use the escape factor, you would be saving space.
Ah, yes.
They're not going to be large.
Okay, yeah, they'd have to be really, really big for you to save space using that approach. Good point. Okay, all good? All right, good. Okay, so here's actually how the whole encoding for 1 key value pair looks. So I talked to you about these shared, unshared bytes, and I talked to you about the key. I'm using this slide just to point out that the size of the value, right? The value is also var length. So you also have to have a var int that tells you what the size of the value is. And then the entire key value pair is just a contiguous sequence of these bits that tell you exactly like how large the key is, how long the value is, and how many bytes are shared with the previous key. Okay, good. Okay, so far we have a nice sequential format that does delta encoding. Do we have any issues here? Well, you know, it was already mentioned. We have a performance issue here. Why do we have a performance issue? Because, well, for two reasons, really. Well, to put it succinctly, we have to potentially decode an entire page to actually get to the key value pair that, you know, our application may be trying to read, right? And this is because, first of all, our key value entries are var length. So, you know, we cannot just kind of randomly access them. But second of all, even if you could randomly access to the location of a particular key value entries, it's sharing prefix bits with previous entries. So you cannot actually tell what the full key is without traversing everything before, right? So, okay, that's annoying. So, and this is usually the problem with compression. Whenever you're compressing things, you're saving space, but potentially slowing things down. Yes.
I'll choose the first key. I see the first key is all compressed and lower bound. But what if like the first key have like the next key have more shortest common prefix with the following keys, and we have to choose a better one.
So what if the next key, sorry, I mean, the keys are sorted, right?
Yes. So what if like the first key we chose just have a less common prefix with the rest?
So basically, like we're at the boundary.
Oh,
Kind of.
but that's okay because you won't be, so the second key won't be, you won't be able to compress the second key that much with respect to the first key by that much, but you'll still be able to encode, like to compress the third key relative to the second key. Yeah, because again, like we're not doing greatest common prefix across all of them. We're encoding each key only relative to the predecessor. So you can still get high compression, yes?
This is page level, or is it like the next page also has on the previous?
Good point. We'll assume here that this is happening just within one page.
Okay.
Right? So that we can still randomly access from storage. Okay. So, right, so this is a problem. We must potentially traverse an entire page. Now, in a database system, you usually have a buffer pool. You might bring one of these pages to the buffer pool, right? But then if you're trying to access the entry, right, every time you still have to potentially traverse the entire page to find the entry. So, so what's the solution? So what are ways of mitigating this issue so that we can still retrieve entries within a page more quickly? Yeah. I need to speak up because of this. So you want to use some pointers.
Yeah.
Okay. But even if we, okay, so you want to use the pointers, but the pointers are not sufficient because suppose I'm going somewhere, I still have to traverse what came before to infer the full key, right? Okay, okay. So yeah, you're basically onto the solution. So the solution, the way that RocksDB calls it, is restarts. Right? And basically what we'll do is take our 4 kilobyte page and divide it into a bunch of restarts. Each restart contains k entries. K is a tunable parameter. Let's say it's something like 16 for here. So each one of these restart intervals, right, contains just 16 key value pairs. And within each restart, you're just restarting the delta compression, right? That's all that it means. Because your data consists of variable length strings and you're fixing the number of keys in each one of these restart intervals can actually be variable length as well. Which, right? And so what we're going to do is store pointers at the end of the page to the start of the different restart intervals. Yes? Pointer to the location. We don't want to store the keys here because the keys are variable length. Yes, that's exactly what we have to do. So that's exactly what this slide is saying. To actually access the correct restart interval that contains the key value pair that you're looking for, you do a binary search over these. And for each hop of the binary search, you actually have to go to the start of the restart, read the key, see if it's bigger or greater, and then continue the binary search over these until you find the correct restart. Yes? No worries.
My question was like, one thing about that is because yeah, keep talking about it.
So, okay, suppose that so each pointer is pointing to the starting location of each one of the restarts, and the start of that restart contains the key. So it's a binary search with one step of indirection. Yeah, you have the whole key here because you restarted the delta compression here. Exactly. Exactly right. Yes. Okay. Good. Questions? All right. I kind of want to speed up. So this allows us to, get faster queries. We don't have to traverse everything sequentially. But, the trade-off is we need moderately more space. Why do we need more space? Because for one thing, we're restarting the delta compression. So we're wasting a bit of space by not being able to compress the first key in each restart interval. And we're also wasting some space for the pointers at the end of the page. But that's not too bad. Okay, so reasonable trade-off overall. All righty. Now let me ask you the question. Can we be even faster? So now we have to do this random binary search within the page to find the entry to the restart that you're looking for. Can we do even better than this?
Finding all binary search is kind of like doing attachments. So maybe you store the first key at the pointer location.
Okay, that's a really nice idea, but that will still be logarithmic, still a binary search in its core. Yeah, let's see. So can strive for constant time. Can we find the restart interval in constant time? The answer is no, but let's try. Yes? Okay, yeah, so let's try hashing. So what would this look like? So yeah, right. So the most naive solution is to take a hash table and map every key in the page to the restart interval. But the keys are variable length, and the keys are also going to take up a lot of space, so we're going to be wasting a ton of space. So that's a simple hash table. It's not really going to work here. We need something a little bit smarter. And this brings me to the topic of the page hash index. Okay, so the page hash index is this other component that we're going to add even after the restart pointers to the very end of the page. Okay, and this is going to be some sort of succinct probabilistic hash table that's not going to store the full keys. All right, it's kind of going to look like some of the filters we've seen, but it's a little bit dumber. And it's dumber because it has to be more performant. I'll talk more about that in a second. But the main idea is this is trying to map each key in the page to the restart that key belongs to, but it's trying to do that without actually storing the key. Okay, so here's what it's going to look like. Let's see how we construct it. First of all, what are the dimensions? Let's suppose that we have this is an array of slots. It just has an 8-bit width. That means that you can identify 256 restarts uniquely, because each one of these, we're assuming that each one of these is just an address of a restart. No worries. Okay, and the number of slots in this array is going to be the same as the number of entries in the page. Okay? Now, all of this will start off being empty. Now, suppose we're in construction mode and we want to add the first key. So we'll add the key. We're going to hash it to some random slot. And we're going to add the address of the restart interval that contains that entry. Right? And we're doing that. And we're not, note that this is for key X. We're not actually storing X. We're just storing the offset of the restart interval that contains X. Does that make sense? Okay. So let's do this again. Now we're inserting key Y, which is in restart offset 2. We're going to hash Y to this slot, put 2 here. What should we do in case of, okay, so suppose we now have this. Key Z can come, and it's at restart 5, and that hashes to some entry, some slot that is actually occupied. We have a collision. What should we do here? Yes.
Earlier, so that you start at 0 point. Get there.
So what do you mean pick the one that came before?
Yeah, lower.
Oh, and like just not put this one at all? Oh, I see. Okay, so I see. You're trying to lower bound it, right? You're kind of trying to go there and then like continue sequentially from where that's actually not a bad idea. And that's actually an idea that I think works better than what it's currently doing. So let me show you what this is doing, and I think your solution might actually be better. Okay, a collision actually cancels the slot in this design. So what does that mean? It means that you add a symbol to the slot, let's say a string of all ones, and it tells you a collision happened in this slot. So if during search an entry is coming to the slot, and we saw that there's a collision, we're actually just going to default to the binary search that we saw before. We're not going to use anything in this hash table. We failed. Does that make sense? Okay, so if we have a collision, we just do a binary search as usual. But if we have a query later on, and the query goes to a slot that is not canceled and that is not empty, then we know that at most one entry mapped to that slot. And that means that, you know, the slot ID, the restart ID there, we know that it's correct. So we can just go there. All righty. Okay. So why did they opt for this design? They opted for this design. You know, you could have handled collisions in this design as well, using some techniques like, you know, maybe the rank and select quotient filter that we saw in the 3rd lecture. You could have done that. But then you would have to potentially, you know, you might have runs of size greater than 1, and you might have to traverse multiple restarts, and also you'd have to, you know, store a bunch of metadata. They did this because this is a really, really simple solution. It's really bare bone. And at the end of the day, they're trying to beat binary search. Right? So if you're trying to beat binary search, you can't be too sophisticated. Does that make sense? Okay. Okay, so these non-canceled slots guarantee that we can jump to the correct restart location. So now we might ask, what's the likelihood that we actually hit a non-canceled slot? What's the likelihood of success? Does anybody have an idea of how we might be able to analyze this? So let's give you a hint. So to analyze it, we need to reason about the number of slots in this array that are empty with only 1 entry, or with more than 2 entries, or sorry, with more than 1 entry. The ones that are with more than 1 entry, those are the canceled ones. How would we reason about the number of entries that are in each of these 3 categories within this array? We've seen this already in the course, actually. Yeah?
And that would be number of keys instead of all the start. And that would be the number of entries in this array. Like what portion of
The number of entries and the number of slots here are equivalent. Remember that. And generally with an array, you cannot assume that you will have a perfect bijection because of collisions, right? So if you have entries and n slots, there will still be probabilistically some slots that are empty and some slots that have collisions. This is what we're trying to answer, right? Assume the number of entries and the number of slots is the same. We have seen how to analyze this. I will give you another hint. We saw how to analyze this in the context of Bloom filters, block Bloom filters. So what distribution allows us to approximate the number of entries that fall into a given bucket in a hash table? The Poisson distribution. So the Poisson distribution with, and we saw, right? We saw this with the lecture and Bloom filters. So the Poisson distribution with lambda parameter corresponding to the bucket size allows us to measure the probability of getting a bucket with, however many entries, like, I entries. And this is, and so here we have as many slots as entries. So we can just use lambda equals 1 to make the approximation. And here are the answers. So, right, so here's how you would model the probabilities for these different events, right? The probability that you just, so, with respect, so you just take the Poisson distribution with lambda and 0 and 1 for the empty and for a slot with 1 entry. And you take 1 and subtract both of these to get the entry of a collision. Right? These are all the different events that can happen and that we care about. And you can actually get very nice, just take the Poisson distribution, plug in lambda equals 1, and this is what you're going to get for these. Okay? Okay, so now we know this. Our overall goal is still to compute the likelihood that we hit a non-canceled slot. So now that we have these, how based on these should we compute the probability of hitting a non-canceled slot? Sorry, 1 minus? But that will also capture the probability that it's empty. You need to do a conditional probability here, because when an entry comes in, you know that that entry, let's assume that it's an entry that we know exists. An entry that we know exists is never going to go to an empty slot. Better idea? Okay, so really in the interest of time, I kind of want to race through because there's still a lot I want to get to before your presentation. I'll just show you. So a given entry that actually exists is either going to land on a bucket with 1 entry or on a canceled bucket where a collision happens. So, if we just condition it based on the probability that it hits a bucket with 1 entry or a canceled bucket, right? We take the probability that it's a bucket with 1 entry, right? And divide that by this. So, so we just do this. And the odds are something like 60%. Right? So the odds are something like 60% that we're going to be successful. Right? And this is kind of cute because, right, you see we're building all of these nice tools that allow us to now do analysis in a range of different cases and to actually very quickly and easily get back of the envelope estimations of how effective a given approach is going to be. Right? So with kind of a 60% chance, we get to just do 1 random access, and with a 40% chance, we get to do the binary search over the page. Does that make sense to everybody? Alrighty. Does anybody have a sense of how you might want to improve this? If you wanted to, yes? Sorry? Yes, that's right. You could use some extra space. And if you use some extra space, you would decrease the probability of collisions, right? And you would be able to model the effectiveness of that using exactly the same analysis, just by changing the lambda. Okay, other ideas? Yeah?
You see either one of them is empty, you can just go to the empty one instead of like causing hash collision.
Yeah, so a more effective hashing strategy for collision resolution might help us too. Yes, it might help us too, but it's going to be more computationally expensive. right? And given that we're trying to beat the binary search at the end of the day, we don't want this approach to be too heavy. Okay, so next week, we're actually going to see something called minimal perfect hashing, which will actually offer some sort of solution to this. Anyway, I want to leave it at this. There are more techniques that I want to get to. So we've done quite a lot. Let's try to see if we can do the remaining 3 in a half an hour. So I want to now move on and talk about LZ77. So this is a very, very widely known and used compression algorithm invented by these 2 gentlemen who actually passed away not too long ago, and interestingly, within a month of each other. And these guys were in the Technion in Israel. And they're both considered to be pioneers of information theory and of compression in general. So the algorithm they created is LZ77. It's from the year in which it was invented. And the idea here, what is our motivation for using this algorithm? So far, all the compression that we've seen was just on the sorted keys, right? But aside from the sorted keys, there's still values, many values in the page. The values might actually be larger than the keys that we're compressing. And so is there a way to actually capture redundancy within the values as well, and not just the keys, to compress the values too? So this is the motivation for using this. And the core thing, so what we're going to do is we're now going to change the view. Up until now, we looked at the page as containing a bunch of key value entries. Now as an outcome of everything we've done so far, let's just look at what we've done so far as like just an array of bytes. And this is how we're going to look at the page for now. So, so now we no longer need to consider boundaries between keys and pages, right? Let's just look at what's left of the page as a string of bytes. And then we're going to use the LZ77 algorithm to compress that whole string of bytes. Okay? Question? No, whole page. So in some sense, we're now completely stacking the LZ77 on top of everything that we've done so far. It's not orthogonal, it's on top. Yes. Okay. So what we're going to do in this algorithm is basically slide a window over the page, and the page is just our input string. And what we're going to try to do is eliminate repeating substrings. That's the core of the algorithm, right? Really in a broad sense. But let me give you the principle in a little bit more of a crisp way. Now I'm only looking at the values that I showed you before, but still, I mean, you should think about this. This is going to be our running example, but just think about this as like a string of bytes representing the whole page. Alrighty, so here is kind of the core principle. Let's consider some substring of the page. This algorithm says that any substring within our given whole input string can be seen in the following format. It can be seen as some other substring that we have seen so far with maybe some space in between, and then a new character. Okay, so that seems a little bit convoluted, but here is exactly what I mean. Suppose I'm looking at this substring here, ELLO. This substring can just be, so as you see, we've seen ELL before, right? So this is some substring that we've already seen. And this new character at the end just says, okay, after the substring that we've already seen, we're adding some new character that we haven't yet seen to the end. Okay, this is basically how the algorithm is going to look at the entire string. And for each string like this, it's going to compose it into a triplet, right? And the triplet is going to consist of the following 3 fields. One of them is telling you how much backwards do you have to go to the substring that you've already seen. And then you also have the length, right? And then you have the new character, right? And based on these 3 things, you can fully infer what the whole string should be. Does that make sense? You have all the information there. Okay, so the way that the compression algorithm is now going to work is it's basically going to run a sliding window over the whole string, and basically transform the entire file into triplets like this. And we're going to see a running example. But there was a question?
Yeah, so I guess in the first case, the question would be, so you're creating triplets, just imagine each of them for the sake of the argument would only contain like 3 bytes. And if none of the characters are repeating, then it's just going to be 0, 0, next character, 0, 0, next character.
Correct.
So in the worst case, again, for the simplicity of the calculation, it's going to be 1 byte and 3 bytes, and pi times like the compression actually ends up being 3 times worse than.
That's correct. So and this is a great point as well. If you don't have any redundancy in your data, this will actually inflate your data. And you will be completely defeating the points of using this algorithm. So actually, so you can tune this. So, if you're a DBA and you know something about your data distribution, you can just say use the compression or not. But actually, I think that RocksDB is smart enough to understand when it's inflating the data and then just aborting the use of compression. Okay. Okay, so here's how the compression algorithm is going to work. Here's a running example. Okay, so we're going to run this window, but this window will actually consist of kind of 2 sub-windows, a search window and a look-ahead window, right? And these windows, they can be kind of overlapping, right? But it's also possible, right? But for the most part, what's actually going to happen is the look-ahead window will appear, right after the search window, and in that way, they're just kind of going to slide. Okay, so this is how much we look ahead, and this is how much we look backwards for a substring match. Okay, so it starts like this, and we're going to initialize a pointer to the start of the string, and just consider this h. And this h, well, it's the first character that we're seeing. We couldn't have seen any matching substring before, so we're just going to output, the following triplet, just says no substring before matches, because we've not seen h before. And we're going to continue doing this, and this is the first time we see the letter E. So also there's no matching substring. And now L, and there's no matching substring. But now we get to the second L, right? And within our search window, there is another L here, right? So this is our first opportunity for compression, but still we don't win that much, right? We can just kind of go to the O here. LO is not something we've ever seen before. So we basically now store this triplet, and this triplet corresponds to this LO here. Okay, and we continue. And now things actually get more interesting. Right now, so now we're looking at this H. Within our search window governs how much we can actually look backwards. We see this H, we've seen an H before. We move onwards. We've also seen an E before after this H, and this continues and continues because we've seen HELL until we get to J. And so once we get to J, that's the end of the substring that we've seen. And so we write this triplet, and this triplet basically allows us to encode 5 characters. Right? So so basically we're actually getting more and more effective as we go along, because as we go along, we will have seen more of the data and we have more of a sense of its distribution, and we can exploit it more for compression. Right, so here is another example. Here I am at E. I've seen this E before. I've seen an L after it. I've also seen an L after it. But this O is the termination of this repeating string. So then I can output this triplet, which corresponds to the last 4 characters. Okay, and then I'll also output one triplet to mark the end of it. That's how the algorithm works. Yes?
So the size of the search is 2.
The size of the search is? 2? Tunable.
Yeah, like the size, it seems like the size like the search.
Excellent point. Excellent point. Yeah. So I was going to talk about that in a few slides, but what does that trade-off control? Right. So indeed, as you say, you can tune the size of the window. What does that control? Performance against what?
When you're compressing now, back even further to get the best match.
That's still about performance. So you're right. So like the longer the window is, the longer back you have to consider more stuff to find a matching substring. So the bigger the window is, the more performance we're losing. But what are we winning if the window size is bigger? Better compression rate, because we have a better window for finding matching substrings. Okay, so it's a compression rate versus speed trade-off. Okay, so LZ77 is actually the backbone for many compression algorithms and libraries that you will see today. So if any of you have heard of Snappy library by Google, LZ4 or ZSTD by Meta, these are all, the foundation of those is LZ77, all right? So if you're in systems, this is an important algorithm to know. Just out of curiosity, who actually knew about this algorithm before this class?
That's because.
Ah, okay, good. Okay, good. So I'm happy this is new for all of you. All right. Okay, so just a few more things about LZ77. How big is the size of each triplet in LZ77? Does anybody have a sense? So you want each one of these to be a byte?
And the offsets are in like one side of your.
Uh-huh. How many?
Like a regular int, so it's like 64 bits or 8 bytes.
Okay, so they could be a little bit smaller. In fact, each one of these only needs to be, it's like the number of bits you need for each one of them is actually, log base 2 of the search buffer size. That's like that's the number of bytes you're going backwards, right? So we're in compression land here, so we're trying to save space. So we just want this to be as small as possible. Right? And the length is going to be equivalent to my look ahead buffer size. Okay, so not too surprising. What about the size? Like, what about this? So far, we've been kind of compressing, we've been looking 1 byte at a time. We could do 2 bytes at a time. We could also do a subset of a byte at a time. What does this control? So how big should this be? Or what trade-off does it control? Okay, so the answer is it's a really good question. Basically, the smaller this is, the more triplets there are going to be. On one hand, the smaller this is, you might have more triplets in your encoded representation. But the smaller this is, this also kind of allows you to do finer grain compression. You can imagine kind of encoding a few bytes at a time, but then you need the string of bytes to be repeating to be able to capture the redundancy. But usually setting this to be something like 1 byte is actually pretty effective. Just wanted you to think about every aspect of the design. Okay, let's move. Okay, what's the runtime with respect to the window size? We just talked about it. It's going to be n, where n is the size of the input times the window size, right? And this gives you a trade-off to play with between compression time and CPU time. Okay. All right. That was LZ77. Good? Any questions? Okay, now let's try to take LZ77 and do even better. So now imagine that you have those sequence of triplets which LZ77 generated. And now, suppose you have the following insights. These offset pointers, you might have some patterns within the metadata in the triplets. Right? So these 5s might be repeating. And perhaps also these lengths, like maybe you're encoding a lot of sequences of a similar length. So there might be some redundancy there too, right? So some of the characters within these triplets might be repeating. And some of the characters might be repeating too, right? Because you might have some characters, different characters occurring with different frequencies. So now this is the thing that we're going to try to reduce and compress. And we're going to do that using a technique called Huffman coding. Huffman coding, who has seen before? Yeah, that's typical. So that's most of you. Okay, so I'll kind of run through this quickly. As kind of a refresher. But the idea with Huffman coding is we're going to reduce frequency. We're going to take frequent symbols, assign them smaller codes, take infrequent symbols and assign them longer codes to overall minimize the overall code length. Okay. Okay. So, and the nature of these two different algorithms of Huffman coding versus LZ77, they're kind of different. With Huffman coding, we're encoding each symbol as succinctly as possible, using that symbol's relative frequency in the whole stream. And with Huffman coding, we're just kind of eliminating repeating substrings. So in some sense, these algorithms are kind of orthogonal to each other. Okay, here is Huffman coding, just for those of you that don't remember. So here's this is an independent example now. I just have a string of characters. I'm going to construct a histogram for how many times each one of the characters appears in the sequence. Is that a question? No, okay. Now, based on this histogram, I'm going to take each one of these entries in the histogram and maybe put it in some sort of priority queue, where the priority queue always spits out kind of the item with the lowest frequency. And then I'm going to start building a tree by connecting sequences of like the least frequent symbols first, right? So the least frequent here are E and D. I'm going to connect them first. The substring is now of cumulative frequency 3 because I add their frequencies, right? And I just kind of continue doing this. I'm going through this fast because you all said that you know this algorithm. But the next thing that I'm going to do is now I have a substring of size 3. The next smaller thing is 8. I'm going to connect those. Next, what do I do next in this algorithm? What's the next step? Connecting B to this? A and B, correct. Exactly right, because both A and B have a greater frequency than 11, than the cumulative frequency of this subtree. And then finally, I'll connect these two. Okay, now I have my Huffman tree. And I am going to remove the frequency labels and mark every left edge and every right edge as 1 and 0 respectively. And now basically the path from the root to every symbol is going to encode basically the code for that symbol. Okay? So that's nice. Here are our final codes for this particular example. Note that this is a prefix code. We've seen prefix codes actually already in the last lecture. But the point of a prefix code is that no code is a prefix of another code. That's really important because that's the property of this code that allows us to decode it unambiguously. All right. Okay. And yes, note that more frequent symbols in the original string actually are assigned smaller codes. That's what allows us to do the compression. And here's a nice feature to know about. Huffman coding actually is guaranteed to be optimal. You can't really, so as long as you're encoding, I'll put it this way, as long as you're encoding one symbol at a time, you can't do any better. There are ways of encoding multiple symbols at a time that will actually allow you to do better than Huffman coding, but as long as you're encoding one symbol at a time, you can't do better than this. All right, what are some of the overheads here? Okay, so to construct this thing, we need to have a priority queue and pop the priority queue. So if we have S unique symbols we're trying to encode, the overall runtime is S times log S. So, okay. So that's the construction time. Okay, so now suppose these are my triplets from the LZ77. I've now done some Huffman encoding of the internal symbols. Maybe I've done that for the characters. Actually, RocksDB uses a library that does separate encoding for the characters, for the lengths, and for the offsets. It will use Huffman encoding separately on each one of them, right? And so this is just Huffman coding for the characters, and I'll then just plug in the codes, and my whole thing is smaller. Okay, so okay. So why do I think this is cool? I think this is cool because we're just taking a bunch of compression algorithms and we're just continuing to stack them on top of each other, right? We started with delta coding, then we put LZ77 on top to also compress the values. And now we're saying that's not enough for us either. So we're going to compress the triplets in the LZ77, right? And all of these just kind of stack up on each other, which I think makes this design very, very interesting. Okay, so what are the trade-offs here? This is going to further improve our compression rate, but this Huffman coding is actually seriously now going to degrade our compression and decompression speed. So building the Huffman tree takes some time, but also now these triplets are not fully aligned. So And we have to do a lot of bit manipulations to actually traverse them. And to decode each one of these codes, we actually need to do that using the Huffman tree. Right? We actually need the original Huffman tree to decode each one of these codes to tell us what symbol it corresponds to. So it makes things a lot slower, but also a lot smaller. But then again, note that it makes things slower in terms of CPU. In terms of overall speed, you might actually still win because the overall thing that you're reading and writing from storage is smaller. Okay, so there's actually some sort of contention with compression here. On one hand, compression is improving your I/O. On the other hand, it's slowing down your CPU. If you're going to do compression too much, you might actually kind of suffer in terms of performance at the end. It's not clearly clear, right? It's like some sort of parabola. Yes.
Compressing like the first two numbers.
Sorry?
We're doing Huffman coding on the first two numbers.
These two?
Yeah.
So I kind of tried to say this. Maybe I wasn't so clear, but so this character, recall that corresponds to like offsets.
Yeah, right.
This one corresponds to length. Well, so the answer was yes. The answer is that like we're going to do Huffman coding separately for all offsets, all lengths, and all characters. Right. So we would still be we can still encode those using Huffman codes. Yeah. Okay, we're almost at the end. I just want to talk about dictionary training. I'll be very, very quick. Okay, so far what we've seen, all the techniques that we've looked at so far eliminate redundancy within a given page. Suppose, but in this application, we have multiple pages. And these pages might actually have some redundancy across the pages, right? So you might imagine the following example. Here, the keys are different, but the values are actually completely repeating, right? So wouldn't it be nice if you could also eliminate redundancy that exists across pages to get an even better compression rate and not have to compress every page from scratch? So does anybody have an idea of how we might do this? Yeah, so we're going to do something like this. Yes. Okay. So the idea is we'll capture redundancy from across different pages in a dictionary. And then the idea is that this dictionary is essentially this dictionary will contain a sample of common substrings that exist across all pages. And we're going to create this dictionary when we're constructing. Okay, I'll talk more about how we create this dictionary in a moment. I'll just say for now that now whenever we actually compress a page using LZ77, we're conceptually going to append that page to our dictionary and then do the compression with our search buffer and kind of encapsulating the dictionary. So our LZ77 will actually take redundancy in the dictionary from the onset. Make sense? Okay. Now it's also for that reason, it's also important for this dictionary to fit in the L1 or L2 caches. So we don't want this to be too big. Yes.
The substring, and then would it also contain the index and the length at which you're able to observe that where that value is originally obtained?
Yeah. So if you suppose you're trying to encode some sort of string over here in the page, you can have a pointer to the back, assuming that the dictionary is right behind you. Right? So here I conceptually took the dictionary and appended the page I'm trying to compress to the dictionary. It's implicitly appended, but like if I have a pointer that's like pointing backwards to longer distance than where the page begins, I can assume that that's actually referring to the dictionary.
So I guess the dictionary might be search buffer, but instead now the buffer is the entire page that you've seen previously.
Yeah, you can say that. Yes.
But would append the dictionary to the page or to each window? Because each window is separate.
It's probably conceptually cleaner to say that we append it to the window. I mean, but like another way of saying it is we only append it during compression, but then we don't actually store the dictionary appended to each page. The dictionary is only stored once somewhere. But it means that in order to decode a page, right? We can't just append it again and then do the decoding. Okay. Okay, I want to finish off because I want to give you a fair opportunity to present from start to finish. Let me just say, last few slides. It could be, you could imagine a dictionary for the entire LSM tree, let's say. But what's the problem with this? The problem is you might have different data distributions, and maybe the data distribution is actually going to shift over time. So that means you might have to update this dictionary. You could maybe have an updatable dictionary. Maybe that's okay, but that's not what RocksDB does. You could also consider having a dictionary per level, right? But then potentially, like, your data distribution within a level is going to vary a lot as well, because the level might be big. Right, and then if you're using this approach, you might train a new dictionary during compaction. What RocksDB is actually doing is it creates a dictionary for every SST. And each SST is like a spatial partition with sort of data of the level, right? And there's basically one dictionary for every SST. That dictionary is actually stored as a part of the file, and it's created during construction time. Like when you're doing compaction, you're going to be sampling the keys that you're compacting and creating the dictionary on the file. Alrighty. And how do you actually create a dictionary? You do that as you're creating the new SST. You're going to take a random sample of blocks. Within these blocks, I'm being very, very high level here. You're going to take k-mers. K-mers are, kind of overlapping strings of different lengths. You will insert those into something called a count min sketch, something that looks like a count min sketch, which we looked at a bit last semester, but this is basically an approximate histogram. And then based on the most common substrings that you see in the sample of blocks, these are the ones that you'll actually put in your dictionary. And then that's your dictionary. Okay, so that gives you a very, very high level. And at this point, we are done and we can do your presentation. So